Hello everyone. Today we're gonna learn 6.6 surface integrals. Okay, so we learned line integrals in 6.2, right? So line integrals we did integrate over a path. So it's one object, one dimension object means that we have a line or path, wire, and then helix, yeah? So that is one dimension object in a plane, XY plane, or in a space, three-dimension space, yeah? Okay, today we are going to learn surface integrals. So this one is integrate over surface with a two-dimension object. So what is a two-dimension object? Think about sphere or cylinder in space in three dimensions or higher dimensions. Make sense? So I'm gonna show you picture later on too. So we have a learning object here, and there's two kinds of surface integrals. One is for scalar valued function, other one has a vector field. All right? Okay. So when we learned about the line integrals, we did a parameterized of the line, right? Of the path. So we did that here too. We do that here too. So we are making parameterization. So let's take a look at the definition here. So they say that given parameterization of surface R of UV and gives that x of UV, y, z. So let's think about just x, y, z. We have UV from there, right? And then the parameter domain, which is other name is a parameter space. So parameter domain of parameterization is the set of points in the UV plane that can be substituted into R. Okay, so what this means? This means the surface lives in three dimensions. The input U and V lives in two dimensions, so flat UV plane. The parameter domain is the region on the two-dimension plane where your formula works, okay? So basically, we might think about R of UV as the function, acting like a function, right? So we input UV, we get output three dimension, yeah? So we input two dimension, we get the three XYZ output, all right? Okay, so we have this this example describes surface as parameterized by R of UV cosine U sine UV. Yeah, U is between negative infinity, positive infinity, and V is negative from the negative infinity to positive infinity. Okay, so this will be cylindrical surface in 3D using two parameters, UV, right? Okay, so we can realize that cosine U, sine U is a circle in XY plane. Yeah, unit circle. So R equal to 1 in the 3D space. Yeah? Okay. Once again, this means input UV lives in the UV plane, two dimension, right? And we call UV as a parameter. We have output x equal to cosine u, y equal to sine u, z equal to v. Make sense to you? In 3D space, of course, because we're using x, y, z. Yeah? It's okay? Okay, so since we have x equal to cosine u, y equal to sine u, we can make their domain u is between 0 and 2 pi because it's a circle, right? And v, which is z, right? We can make negative infinity to positive infinity. Yeah. Okay, let's take a look at this one. So this one, they just giving us when k equal to 0. So I want to make a k, right? Yeah. They were using new. Why change k? I just follow that. Sorry about that. All right, so k equal to 0, cosine 0, sine 0. So we calculate, then we have 1, 0, v. Means that v is any number, right? So x equal to 1, looks like 1 is here. X equal to 1, y equal to 0. V can be any number, so there is a line. Make sense? Okay, when k equal to pi over 2, and cosine pi over 2, sine pi over 2, v, then we get 0, 1, v. So 0, 1, v. Yeah? V is any number, so it's a vertical line as well. Make sense? So rest to, we can do that. When k equal to negative 2, so we plug in cosine negative 2, sine negative 2, then we get approximately 1, 0.03 and negative 2. So it's over here 1, negative 0.02 and negative 2. Yeah. So plot the point here, and then we plot the point rest, connect, we get the circle there, right? Okay, so we knew that x equal to cosine u, y equal to sine u, then we can express x squared plus y squared equal to 1. So it's a cylinder in 3 dimensions. Yeah, 2 dimensions we said a circle. In 3 dimensions we said a cylinder. Okay, now if we change the parameter, so this picture is about x squared plus y squared equal to r squared. And then the parameter domain, u is between 0 and 2 pi, and v is all real numbers. Now, if we change the parameter domain from u is between 0 and pi, we cut in half, right? And v is between 0 and 6, then I drew this one from Calc3D website. So that is a half cylinder, right? So you guys understand what we are doing. Half cylinder of height 6. Yeah, makes sense? This one is z, which is height. Yeah. All right. Okay, so we have a definition here. Parameterization is a regular parameterization if the cross product of R sub u and R sub v there, right? Okay, so this means partial derivative with respect to u because we had a f of x, yeah? F sub x, sorry, f sub x, right? So this means, let me write down. So think f sub x, partial derivative respect x, yeah? And then we have f sub y, partial derivative with respect to y, and so on, right? So we have that, the cross product of the partial derivative with respect to u and partial derivative with respect to v is not equal to 0 in the parameter domain, right? So that is a terminology. By using the terminology we have smooth, yeah, smooth when the cross product of partial derivative with respect to u and partial derivative with respect to v is not 0, right? We say they're smooth, yeah? So then we can say the regular parameterization and also smooth, right? Okay, now let's take a look what is not smooth. What is a smooth, right? So this is we called torus, which is donut shape. We say that this is smooth, and this is a pyramid, right? So this is not smooth because there is a sharp here, right? On the vertices. So we called piecewise smooth because inside is smooth, but not in the vertices. Yeah. Okay. All right. Now we have derive the formula. Yeah. Okay. So we have little rectangle here from the UV plane, right? Then we send the two mapping from the R of UV, right? Then in 3 dimension, we have the piece there, right? Okay, now we have a tangent vector. So tangent vector, we have partial derivative with respect to u. So I want to express as dr over du. Means that partial derivative, then we have a u direction. So we have f sub x, partial derivative with respect to x, then that's x direction and the y direction, z direction, right? And we have a dimensional derivative earlier in the sections, right? Okay, now we have a tangent vector. So basically we knew the tangent vector just touch, right? So from this point, we have a tangent vector this way, we have a tangent vector from that way, yeah? So there is a partial derivative with respect to u direction. So that way, we have a partial derivative with respect to v direction, yeah? Okay, so we have two tangent vectors there. If we have a cross product of two vectors, then we say that normal vectors. Yeah. Okay. So normal vector means perpendicular to the surface in that case. All right. Now, how do we approximate the area of a surface then? So from here, right? So this is the one. Okay. Now, we have the magnitude of cross product. Then we learned from, I don't remember, the 3.1, something like that. Cross product, yeah, cross product, right? So end of cross product, we learned magnitude of cross product is area of a parallelogram, right? So here we go. Okay, then we times width and height. The delta U, delta V is width and height from that rectangle. Yeah. Okay. So we can derive the formula. Take a look. So we have double integration means that area, right? Okay. So we are using the magnitude of partial derivative respect to u for the tangent vector, and partial derivative respect to v from the tangent vector, right? So we make a cross product, and then we make a length. So dA will be dv du, right? So I'm sorry, the delta u delta v, right? So height times width. So we need the tangent vector of u. So that is the r over du, which is partial derivative with respect to u. So r has x, y, z. So we can express partial derivative with respect to u from the x equation, partial derivative with respect to u from the y equation, and partial derivative with respect to u from the z equation. Make sense? Okay, so we have an example show that the surface area of sphere x squared plus y squared plus z squared equal to r squared is 4 pi r squared. Okay, so from the spherical coordinate system from the earlier section, in the beginning section, right? We have x equal to r cosine theta sine phi, y equal to r sine theta sine phi, and z equal to r cosine theta. Theta is between 0 and 2 pi, phi is between 0 and pi. It's given, right? Okay, now how do you find the partial derivative respect to phi of tangent vector, right? So I wrote down the formula here, and then we can just find cross product of two vectors, but then we know that the cross product is not the commutative, right? Their sign changed, right? But then later on we get magnitude. So it's not really matter, even though the swap the order, right? Okay, so let's do that. Let's find out partial derivative with respect to phi. Okay, that means we're looking at the first one, x, and partial derivative with respect to phi, and theta, r is constant, right? So there will be cosine phi, and then we keep that, yeah, because constant. Okay, so r cosine theta cosine phi. Okay, we're looking at the y partial derivative with respect to phi, same, right? So cosine phi, so we keep the sines, r sine theta and cosine phi. Okay, now we're looking at the z partial derivative with respect to phi. So we have r negative sine phi, yeah? Okay, now we do partial derivative with respect to theta. So theta, then first one looking at cosine theta, which is negative sine theta. And then we keep that as a constant. So r negative r not cosine, sine theta and sine phi. And second one, r cosine theta sine phi. Yeah. And then third one, there's no theta, it's 0, right? Okay, cross product. Okay, so cross product, a lot of work. Okay, so we make a cross product of, okay, so I, J, K, yeah. All right, so Let me write down. We have r cosine theta, cosine phi, and little bit move here, and j. Second one, r sine theta, cosine phi, negative r sine phi. Yeah. Second one, negative r sine theta sine phi. I'm doing this one, right? Then r cosine theta sine phi and 0. Yeah. Luckily we have a 0. Okay. So let's make I. Okay, we know that plus minus plus. I mean, the bottom, yeah. So we have a plus, minus, plus. Okay, I plus j. Sorry, negative j. Negative j plus k. Okay, so I, luckily 0. So 0 minus is positive. So 0 plus r squared cosine theta. Hey, no space. So we keep this one, right? So multiply this way, then minus this way, and positive r squared cosine theta sine square phi. Yeah? Sine square phi. And g, we're looking at that. So we multiply 0 minus, and then we have r squared minus minus is positive. So sine, hold on 1 second. Sine theta. So r squared sine theta sine square phi, right? Okay, third one, we're using this one. Okay, so that will be r cosine square theta cosine theta sine theta, right? So we have that will be long, so I'm gonna write down r cosine r squared cosine square theta cosine theta sine theta minus and plus r squared sine square theta cosine theta sine theta. Yeah, it's the k. Okay. Let's just simplify this one. So we have r squared and cosine phi sine phi. We can factor out, right? Then we have a cosine square theta plus a sine square theta. Can you see that, right? So we knew that this is 1. So we can have that, the k term. So there will be r squared cosine phi sine phi. Yeah? Okay, let's make a magnitude. So we will have magnitude of a tangent vector, partial derivative with respect to phi, and the cross product of tangent vector, partial derivative with respect to theta. Okay, so there will be I squared. So we will have r squared cosine theta sine squared phi squared plus r squared sine. Wait a minute. We get the negative, right? Because we have a negative, but it does not matter because we will square that later. So minus theta sine squared phi squared. Sorry, there is no space. And plus inside, yeah. And r squared cosine phi sine phi squared. Yeah. Okay. Now, so first term, so we have r to the fourth power, cosine second power, sine to the fourth power, right? Phi plus r to the fourth power, sine square, and then sine the fourth power, phi. Sorry, no space. Okay, then r to the fourth power, cosine square phi, or sine square phi, yeah? Okay, let me see how we can combine it. Okay, so we can factor out r to the fourth power sine to the fourth power of phi from two terms. So we will have r to the fourth power sine to the fourth power of phi. Then we have a cosine squared theta plus a sine squared theta and plus r to the fourth power cosine squared phi sine squared phi. Yeah. Okay. We notice that this is also 1. So we will have r to the fourth power sine fourth power phi plus r to the fourth power cosine square phi sine square phi. Yeah. Okay, now we can factor out with r to the fourth power sine square phi. Then sine square phi remain plus cosine square phi remain. Okay, so we notice that this is also 1. Okay, then there will be r squared sine phi then. Yeah. Oh, you cannot see, or you can see. Now we want to find the surface area, right? So we had the formula. So magnitude of. So we using this way, right? Okay, so there will be we can put either one, phi first, theta first, it's okay. So let's do using theta, 0 to 2 pi. In the beginning, we had a domain, right? And phi was 0 to pi, right? And the magnitude of that will be r squared sine phi, then d phi d theta. Yeah. Okay. Now we want to integrate this one first. And there is no theta, so I don't have to say that theta treat as constant, right? So we have theta equal to 0, theta equal to 2 pi. R square is a constant, so we have a constant. What's the integrator of a sine? So negative cosine. Okay, so we have negative cosine phi, and then we want to evaluate from 0 to phi equal to 0 to pi. Excuse me, d theta, right? Okay, so there will be theta equal to 0 to 2 pi negative r squared cosine pi minus cosine 0 d theta. Okay, so there will be theta equal to 0, theta equal to 2 pi negative r squared cosine pi. What do you get? It's negative 1. Cosine 0, it's 1 d theta. So we have negative 2 and then positive 2, right? So we have a positive 2r squared d theta. Now we want to integrate respect to theta. So 2r squared theta, theta equal to 0 to 2 pi. So we have a 2r squared theta, which is 2 pi, which is a 4 pi r squared. It's designed, right? So they wanted to find the surface area. This is just a formula for surface area of sphere, right? Okay, very good. Okay, so we introduced in the beginning, surface integral has two types, right? One is a scalar valued function, and other one is a vectored valued function, right? So let's take a look at the formula. Okay, so I want to introduce the line integral for the scalar valued function. We are using that, right? This is familiar with you, right? Okay, so we are using same formula here. So surface integral, we are using that. But then instead of r over t, we are using two parameters, right? So which is uv, right? Okay, so in that case, magnitude of r prime over t, that is the tangent vector, right? So we're using cross product of the magnitude of the tangent vector here. Okay, so instead of dt, we are using the times width and height. We did that earlier, right? Okay. Okay, so let's do this example. We have a surface integral. Find the surface integral. And that function, constant function with that parameterization, u is between 0 and 2, v is between 0 and u, right? Okay, so we want to use this formula, but then there is no function, means that we have a constant function 5, so we really don't have to substitute r into the function, right? We just need to find what's the magnitude of cross product of partial derivative with respect to u and v of tangent vector, right? Okay, so let's do that and then integrate, of course. So let us do that. Tangent vector first, right? Let's do that. You want me to write down the formula? We okay, right? All right, so let's do that. We're looking at everything respect to partial derivative with respect to u, right? Okay, so what do you get? So 1 2u 0. Yeah. Okay. How about partial derivative with respect to v? So we're looking at every component partial derivative with respect to v. Yeah. So 0, 0, 1 then. Yeah. Good. Okay, now magnitude. So basically this is the vector, right? Cross product. I did not do the cross product. So cross product first. Okay, so I, J, K, we have a lot of zeros, which is good. And 0, 0, 1. So I, so 2u, right? And J, 1. Can you see that? K, 0. Yeah. Okay. Now, magnitude of the cross product of that. So we have a 2u squared plus -1 squared. So we will get 4u squared plus 1, right? Okay, now the function. Yeah. Where's the function? Yeah, we have this one. Come on. Okay, no patient. All right, let me write down. So we have double integral of s 5ds. Okay, so we kept that the constant, and then the limit, this one first, and this one second, because number, right? So u equal to 0 to 2, and v equal to 0 to u, right? Okay, now we have the magnitude of the cross product of the tangent vector, right? Okay, now we have square root of 4u squared plus 1 du. Okay, du dv. I'm sorry, dv du. dv du, right? dv du. Okay, now we want to integrate this one first, right? That means we treat u as a constant, right? Okay, then this is a constant. Yeah, everything is constant. Then we do integrate respect to v. So we have a v of that, right? Okay, easy. So we have 5u from 0 to 2. So v of constant. And then we want to evaluate from v equal to 0 to u du, right? Okay. Now we have 5v. So we keep the constant for u squared plus 1, v, which is 2. No, sorry. V equal to u, right? So we have u. And then I need to integrate u from 0 to 2 du. Yeah. Okay. So we integrate respect to u, right? All right. So if you notice that what's the derivative inside, right? So we derivative inside, then we can see that AU. We don't have A, so we make 8 outside. Or you can use substitution, right? So let U equal to 4U squared derivative. Oh, UU. That's not good. So you know what I mean, right? So you can use that. So A, we cannot use V because A, A, AU, DU, and one ADA equal to UDU. Yeah, please do that. Okay, now that square root will be 1/2. Integrate, we get 3/2, right? So we have 5/8, 3/2, which is 2/3. And then we have 4U to the second power plus 1, 3/2. And then we want to evaluate from 0 to 2. Okay, so there will be, we have a 4, so we have a 5/12. Let's do that. 4 times 2 square plus 1 to the 3/2 minus 0, 1. Yeah, so we have 1 there. Okay, what do you have? Can you please calculate? So do you get 28.79? Thank you. Okay, so let's take a look at this example. So we have a flat sheet and shape in the surface is equal to that. Lies a rectangle between X and Y. The density of the sheet is given by that. So what is the mass of a sheet? Sheet, right? Okay, now we check that M equal to double integration of S, just following the formula, which is x squared y z ds. Yeah, the density function. Yeah, okay. So ds, let me show you one more time. So we have from scalar vector function, this ds corresponding that, and this ds corresponding this one. Yeah. So magnitude of cross product of a tangent vector, and we deal with the 2 parameters. So tangent vector has a derivative with respect to u and v, right? And then dA will be du dv. Yeah. So we're gonna do that. So tangent vector first. Okay, so we have a given function here, z equal to 1 plus x plus 2y, right? Nothing else. So we can set it up r of xy equal to x, y, then this is z, yeah? Z, that is x, y, 1 plus x plus 2y. Make sense? Okay, let me do it. So let's make a note. So r of xy instead of ru, no, uv. Then we can make x, y, z, that is x, y. What's the z? Z is 1 plus x plus 2y. Then x is between 0 and 4. Y is between 0 and 2, right? So let's using that. Copy, paste, and here. Okay. Now, tangent vector, right? So T of u, not u, in the case T of x. So we're looking at this one, partial derivative with respect to x. So first one is 1, second one is 0, and third one is 1, right? What about partial derivative with respect to y? First one is 0, second one is 1, third one is 2. So 1, 0, 2. Okay, cross product. Audition. Okay, there will be I, J, K. So 1, 0, 1, 1, 0, 2. Okay, now I, 0, yeah. J, J 2 minus what? K 0. Yeah. Okay, now let's confirm. So we have J 2 minus 1, right? Okay, so we will have -1. Let me double check. Yeah, you guys noticed that, right? So I made a mistake, right? So partial derivative with respect to y. So 0, 1, 2. Yeah, not the 1, 0, 2. That's why. 0. Okay, one more time. So we have 0, 1, 2. Yeah? 0, 1, 2. So 0, 1, 2. Okay, let's do one more time. I 0 minus 1. Yeah. Minus 1. And J 2 minus 0. And K 1 minus 0 is 1. Yeah. Okay, so we got that minus I minus 2J plus K. Okay, how about length? I hope there is no mistake. So we have 1 square plus 2 square plus 1 square. So we will get 4, 5, 6. Oh, okay. Right. But then Boom made a mistake with this one. Boom made a mistake here. Yeah. Okay, so we have 6. All right. So let's do integrate. So mass, which is S, we have x squared y z ds corresponding the magnitude of this, and then the x dy, right? All right, so which number? We can use either one, right? Okay, let's follow textbook so that we can check the answer. So we have x equal to 0 to 4. And we have x equal to y equal to 0 to 2. X squared y z earlier we have 1 plus x plus 2y, right? So 1 plus x plus 2y dy dx. So we want to integrate to respect to this. So we have x equal to 0 to 4. Then x is constant, right? So treat x as constant. Okay, little bit algebraic word need. Okay, so we want to distribute, so we have x squared y plus x to the third power y plus 2x squared y squared. Okay, so now we do integrate respect to y. So we have x squared y squared over 2 plus x to the third power y squared over 2 plus 2x squared y to the third power over 3. We want to evaluate from y equal to 0 to 2 dx. Okay, so there will be x equal to 0 to 4 x squared 2 square over 2 plus x to the third power 2 square over 2 plus 2x squared 2 to the third power over 3 dx. Okay, so we can simplify. No. Okay, so there will be 2x squared plus 2x to the third power plus that will be 16x squared over 3, yeah? Dx. Combining like term. This one, common denominator, so we get 22 over 3, x to the second power. Okay, now we integrate, right? So there will be 22, 3, x to the third power over 3, plus 2x to the fourth power over 4, from 0 to 4. Oh, missed that. Oh my gosh. Square root of 6. That is this one, right? So magnitude of tangent vector, cross of tangent vector, yeah? So that should be here, right? Ooh, good thing I realize right now, right? So we can put square root of 6 then outside. Square root of 6. Okay, now substitute. So we have a square root of 6. We have 22 over 9 and 4 to the third power plus 1/2 4 to the fourth power, right? Now your turn. I did everything. Can you please calculate? Can you check that? This is 696.74. Yeah, good job. Okay, so we have second surface integral about the second type, I meant. So vector field. Okay, so we had earlier scalar valued function, and this is a vector field. Okay, so we have double integration S, the vector field dot product of ds equal to, we can express this way, right? Okay, so this means let me read this one first. It's a flux of the vector field across the surfaces. Yeah, this is the surface. As we have like a flux of vector field across the curve C, same as this one. Yeah. So basically double integration of a surface, right? Same as the curve C with a one integration, right? Okay, so this one, I want to derive the formula. So we can express as F dot product with N. And we can, it's a unit normal vector. So I want to express as this way. Cross product of that. Yeah. So there is a U. I mean, no, sorry, normal vector. Yeah. Unit normal vector. Yeah. Okay. Then ds there. Okay, so we had this one earlier, right? So we want to substitute the parameterization there. So in that case, it's R of UV, right? So we have change to and then F of R of UV then the product with oh, okay. So okay, so this is a surface. This is a parameter domain, right? So okay, now ds we can express as the magnitude of cross product of a tangent vector, right? dA, right? So there will be, so we have this will be in dA. Yeah, so dA will be du dv. Yeah. Okay, now we can simplify. So we get this. That's it, right? And dA. Yeah. Okay, so this is the last question. So calculating the surface integral of that. Okay, so we are using the formula here. That formula. Okay. There's dot product between there. Copy. That, right? Okay. Now, we want to substitute the parametric function R over UV into the vector field, right? Okay, so there will be R over UV, so negative Y, so this is X, Y, Z, yeah? So X, Y, Z. So if we have a negative Y, so we put the negative, then, so negative V squared, positive U, right? Okay, so there will be positive U. Okay, now X is U, I'm sorry. Crazy, man. Crazy. All right, so once again, minus positive u, and then I didn't complete, right? So positive u minus v squared, right? And then x, which is u, and then last one is 0, so keep the 0. And dot product with cross product of tangent vector, right? Okay, now let us do this one. We're looking at the u, right? And then partial derivative with respect to u, right? So we're looking at the r, partial derivative with respect to u. So what is this? That's 1, negative 1, 1. Yeah. Okay. What about partial derivative with respect to v? 0 to v and 1, right? Okay. Now, let's write down the cross product. So we have I, J, K, and then we have 1, negative 1, 1, 0, 2, V, 1, right? And that will be, so we get negative 1 minus 2V, J, we get 1 minus 0, right? So it's negative J. And K, we get 2V. Okay, then that's it. Yeah. Okay, so let's find out the limit. It does not matter which is the first because both they have a number, right? So let's follow du dv. So u equal to 0 to 3 and v equal to 0 to 4. Okay, so there will be v equal to 0 to 4, u equal to 0 to 3. We have u minus v squared, u 0, and negative 1 minus 2v, and j negative 1 and 2v, and du dv, yeah? Okay. Dot product there, so we multiply component with a component, right? So there will be v equal to 0, v equal to 4, u equal to 0, u equal to 3. So first term with the first term, so u minus v squared and negative 1 minus 2v, and second term negative u, third term we have a 0, yeah? So du dv. Okay, so let's using multiply. So v equal to 0 to 4, u equal to 0 to 3, right? So first term. So we have negative u, second term minus 2uv, third term positive v squared, and the last term positive 2v to the third power, and negative u du dv, yeah? Okay, now combining like term, we have this square, so negative 2u minus 2uv plus v squared plus 2v to the third power, right? Okay, so du dv. All right, that's it, right? Okay, now we do integrate with respect to u. Then we treat V as constant. So there will be V equal to 0 to 4. So negative 2u squared over 2 minus 2u squared over 2. V is constant, plus constant, so V squared u, plus constant, so 2v to the third power u, right? And then we want to evaluate from 0 to 3 dv, yeah? Okay, so there will be V equal to 0 to 4. So negative 3 squared, 3 squared as well, and V plus V squared times 3 plus 2V to the third power 3, and the rest is 0 and dV, right? Okay, so we have V equal to 0 to 4, negative 9 minus 9V plus 3V squared plus 6V to the third power dV. Now we do integrate respect to V. So negative 9V minus 9V squared over 2 plus 3V to the third power over 3 plus 6V to the fourth power over 4. We want to evaluate 0 to 4. Okay, so there will be negative 9. Your turn, please calculate. 9 over 2, 4 squared plus 4 to the third power plus 3 over 2, 4 to the fourth power. The rest is 0. Okay, so did you get 340? All right, good job. Thank you so much. Thank you for watching. I will see you in the next video. Bye.